The hidden force in tornadoes. When most people think about tornadoes, they imagine the funnel cloud, an ominous column reaching from the sky to the ground, tearing apart everything in its path. But what most don't realize is that this swirling vortex doesn't act alone. Hidden within the storm that spawns it is another critical player, the rear flank downdraft, or RFD. The RFD is an invisible hand shaping whether a tornado will form, how powerful it becomes, and how long it survives. It's the storm's secret driver, the behind-the-scenes mechanism that can transform an ordinary thunderstorm into a catastrophe. Without the RFD, many of the world's most violent tornadoes would never have been born. Anatomy of a supercell. To understand the RFD's role, we need to zoom out and look at the storm that creates it, the supercell. Supercells are the kings of thunderstorms, towering tens of thousands of feet into the atmosphere. They contain three main moving parts: a mesocyclone, the rotating updraft at the storm's core, a column of rising, spinning air that stretches toward the stratosphere; the forward flank downdraft, FE, a wedge of cooler air and heavy precipitation that falls on the storm's forward side; the rear flank downdraft, RFD, a pocket of descending air on the backside of the mesocyclone, which curls around it like a scythe. These parts work together in a delicate, violent dance. The mesocyclone creates rotation aloft, while the RFD is often the final nudge that brings that spin down to the surface. How RFDs form. RFDs don't just appear out of nowhere. They're born from the storm's internal processes. Evaporation cooling. As rain and hail fall into drier air behind the storm, they evaporate. This process sucks heat out of the air, leaving it colder and denser, which forces it to sink. Precipitation loading. The sheer weight of millions of gallons of rain and ice in a storm core drags air downward like a lead weight. Pressure dynamics. Rotation in the mesocyclone creates small but powerful pressure imbalances that accelerate air downward. All of this results in a sudden burst of air slamming toward the ground and then spreading outward. In many cases, this air curls cyclonically around the storm's updraft, wrapping like a spiral staircase. The visual signs of an RFD to trained observers. The RFD leaves subtle fingerprints in the sky. A clear slot, a strange hole of blue or brighter sky near the rotating base, signals that dry descending air has carved through the storm cloud. Rain curtains, curved sheets of precipitation wrapping around the storm's backside, often mark the RFD's outflow. On the ground, people sometimes feel a sudden blast of wind, often from the west or southwest, moments before the tornado appears. For storm chasers, spotting these signs is a chilling moment. It means the storm has entered its most dangerous phase. RFDs and tornadogenesis. The RFD's most crucial role is in tornadogenesis, the process by which a tornado is born. When the RFD hits the ground and curves around the mesocyclone, it creates a zone where inflowing warm, moist air slams into descending cool air. This clash intensifies low-level rotation. The mesocyclone's spin is tightened and stretched toward the ground until a funnel finally connects sky to surface. But here's the subtlety. Not all RFDs help tornadoes form. Their temperature and moisture are the deciding factors. If the RFD air is too cold, it undercuts the storm's inflow, cutting off the tornado's fuel supply before it can organize. If the RFD air is mildly cool, it blends with inflow in just the right way, tightening the vortex without suffocating it. This razor-thin balance is why forecasting tornadoes is so difficult. Two storms can look nearly identical on radar, yet one will produce a deadly tornado while the other fizzles out, all because of differences in the RFD. The RFD and tornado strength. Once a tornado is on the ground, the RFD continues to play a decisive role in shaping its strength and longevity. A steady, balanced RFD keeps warm, moist air flowing into the storm, allowing the tornado to grow wider and stronger, sometimes reaching EF4 or EF5 intensity. A sudden cold RFD surge can choke off that inflow, collapsing the tornado in minutes. Case studies of RFDs in action history provides clear evidence of the RFD's influence. Moore, Oklahoma, May 3, 1999. This EF5 monster, with winds over 300 miles per hour, was accompanied by a dramatic RFD clear slot visible to chasers. Its structure likely enhanced the tornado's growth into one of the strongest ever measured. Tuscaloosa, Birmingham, April 27, 2011. A deadly EF4 was shrouded by rain curtains wrapped by the RFD. Many residents never saw the funnel until it was upon them, leading to devastating casualties. El Reno, May 31, 2013. The widest tornado ever recorded, -2.6 miles across, showed complex RFD surges that created multiple vortices. The tornado's sudden shifts were so unpredictable that even experienced storm chasers were caught off guard. These cases show that the RFD doesn't just help form tornadoes, it can dictate how destructive and deceptive they become. Experiencing the RFD on the ground for people caught in storms. The arrival of the RFD can feel like a storm within the storm. Survivors often describe a sudden wall of wind, colder and harsher than the air before, hail and blinding rain slamming sideways, an eerie greenish light as the sky clears briefly in the slot, followed by the roar of the tornado itself. Storm chasers often note that when the RFD wind hits their vehicles, they know the clock is ticking. Within minutes, the tornado will either form or intensify. Radar and research. On radar screens, the RFD is essential for identifying dangerous storms. As it wraps precipitation around the mesocyclone, it creates the classic hook echo, one of the most iconic radar signatures in meteorology. With Doppler radar, scientists can also detect velocity couplets, spots where inbound and outbound winds are right next to each other, a hallmark of rotation near the ground. These signatures, often influenced by RFD behavior, are what trigger many tornado warnings. Field studies like VOR-TXI and IDI sent mobile radars and probes directly into storms, capturing unprecedented data on RFD winds, temperatures, and patterns. These findings confirm that the RFD is usually the final ingredient before a tornado touches down. Why RFDs remain a mystery. Despite decades of work, many questions remain unanswered. Scientists still debate why some RFDs are warm and supportive while others are cold and suppressive. How microscale turbulence within the RFD determines whether rotation organizes. Whether real-time temperature and humidity sensors could one day let forecasters distinguish tornadic from non-tornadic storms. These unanswered questions are part of why tornado prediction remains one of meteorology's toughest challenges. The future of RFD science. The frontier of storm research is pushing deeper into the RFD. Drones are now being deployed to sample downdrafts directly, measuring temperature and wind at scales too small for radar. High-resolution supercomputers simulate RFD formation in stunning detail, allowing scientists to rewind and replay tornado outbreaks virtually. Artificial intelligence is being trained to analyze radar data in real time, picking up subtle RFD signatures that human forecasters might miss. The ultimate goal is to give people more than just minutes of warning, perhaps half an hour or more, by understanding exactly when and where RFDs will drive tornadoes. Why the RFD matters. The RFD may not appear in dramatic news footage. It doesn't get the attention the funnel cloud does. But make no mistake, it is the tornado's secret weapon. It decides whether storms stay storms or become killers. It fuels the vortex, cloaks it in rain, and sometimes extinguishes it entirely. For scientists, decoding the RFD is not just an academic pursuit. It's about saving lives by unlocking the hidden mechanics of Earth's most violent storms.